Starting to record. So welcome back, everyone, to another exciting adventure of Math 140. I've given up trying to remember which lecture we're in. I don't think we are, because I tried to put up last time. I know I called it 14, but I went on YouTube. There was no 13. So I put it up as 13. So I think today is 14, but maybe I missed one. I don't know. But I'm going to put 14 again. 15. Math 140. Is it 15? 15. Well, what the hell? Okay, fine, 15. It's just the next one after the last one. Oh, Angel, how are you?
Good, how are you?
Haven't died yet. Thanks for asking. Angel, I'm going to call you on time, even though technically we just started, but you made it by seconds. So today, chapter 17, the other half of the 17 pair of chapters. 16 is on the basics of confidence intervals, and 17 is on the basics of tests of significance. These are the two main parts of this class in regards to the second half, which we're now in. Confidence intervals and tests of significance have a lot of similarities and some very important differences, of course, as well. So let's recap for a second about a confidence interval. In the case of a confidence interval, you have no idea what a parameter is. So you take a sample, it gives you a value, and then you form an interval around that value. And then you say with some confidence whether or not you believe that the true value is somewhere in that interval, correct? This is the idea behind a confidence interval. You have no idea what it is. So you create an interval and then claim with some confidence that the interval has caused. Yes?
Are you allowed to use the word range?
Well, I don't think the police are going to come and stop you.
I mean, like, is there a remote difference, or they just chose to use interval instead of range?
Well, range has slightly different meanings in math, so interval is better. It is an interval of numbers. From here to here, we call it interval. So interval is better. So what exactly is a test of significance? In a test of significance, there is a value for the parameter that up until that point has been believed to be valid. For example, if I give you a coin and I say, hey, I really don't think this coin is fair. I'm going to test it to see whether it's fair or not. Up until I test it, do I have any reason to believe it's not fair? So up until that point, is there a value for the proportion of heads that I might get that I would believe to be valid?
Yes.
0.5, right? And I'm going to test to see whether or not the data supports that. So in a test of significance, you have two hypotheses. You have the original hypothesis called the null hypothesis. The null hypothesis, labeled H0, is essentially the original belief, I before E except after C. That doesn't look right, does it?
It's I.
It is IE, right? I before E except after C. Okay, so that rule doesn't hold here, does it? You have the original belief, or you have the status quo. In other words, up until now, what did I think it was? What would it be if there was no change? And then you have what's called the alternative hypothesis, labeled either HA or H1, depending on the book that you're using. And it's the new belief. Oh, I'm sorry, I don't think your coin is fair. I think the proportion of heads is going to be 80%, or maybe just more than 50% or something. And I'm going to test that. And I want to see whether the data supports the original hypothesis, or does the data support the alternative hypothesis? Yes.
The first one is H0.
H0, called the null hypothesis.
HA
or H1. It's either 0, 1 or OA. So H0, H1 or HO, HA for original and alternative Yes,
So the second one is the alternative hypothesis?
yes. The second one is the alternative. It's the new belief. It's what you are testing. What you are testing. And the first thing you should realize when it comes to tests of significance is that we never want to use the word accept. We don't accept this hypothesis. We don't accept this hypothesis. We either reject it or we don't reject it. Much like if you go to court. Anyone here ever get tried for murder or some like serious crime? Okay, you, okay, good. Okay, so if you're tried for, if you go to court, do they ever find, yes, we the jury find this person innocent of this crime? Has it ever happened in the history of the American judicial system?
Yes.
Not a single time.
They just say not guilty.
They say not guilty. Either the evidence finds the person guilty or the evidence does not find the person guilty, but they never say innocent. Okay, innocent until proven guilty is nonsense in America. It's guilty until proven innocent. Because in order to find you not guilty, basically we're saying the prosecution has to lose in a sense. The status quo is that you're guilty, otherwise why would you be here? Does the evidence support one belief or does the evidence support the other? So in the language of statistics, we would either reject the null hypothesis in favor of the alternative, or we would not reject the null hypothesis in favor of the alternative. But we never accept anything. No matter how convincing the belief, the data is, 1 in a gazillion chance, we still either reject one or not reject one. We do not accept it. So in this class, we are going to have essentially 2 types of tests. Tests about proportions and tests about means, much like for confidence intervals. We had confidence intervals about proportions and we had confidence intervals about means. But even when it comes to proportions or means, there's still a few different possibilities for what the hypotheses might be. In this class, the null hypothesis always gets an equal sign. The null hypothesis always gets an equal sign. So if I come in and I say, I have this coin, I'm not sure if it's fair or not. I want to run a test to see whether or not it's fair. The null hypothesis, the status quo is, well, until you have evidence against the fact, we're going to assume it's fair. And if it's fair, what is the true proportion of heads that I would get if I kept tossing this over and over again? 0.5. So my null hypothesis would be that the true value P is equal to 0.5. If it's not 0.5, hopefully my data will support that fact. But when it comes to alternative hypotheses, there's actually 3 different types that we will deal with in this class. If it's not 0.5, if you say, no, this is not fair coin. I can make that claim in essentially 3 ways. I can say, no, sorry. It's really somewhat greater than 0.5. Or I can say, sorry, I don't think it's 0.5. I think it's
Greater.
less than that. We already had greater, less than 0.5. Or maybe I'm a little less confident than where it is. I know it's not fair, or I think it's not fair, but I'm not sure which way. So I'll say, sorry, I don't think it's 0.5, but rather, thank you, not equal to 0.5. So in our class, the 3 different types of alternative hypotheses are going to be greater than, less than, or not equal to. Now, when it comes time to actually run the test, we always run the test under the assumption that the null hypothesis is true. We're basically saying, well, if the null hypothesis were true, then this is what I should get. Did I get it or not? If I got it, why would I reject the null hypothesis? If I don't get it, hey, maybe the null hypothesis is wrong. So we always run tests under the assumption that the null hypothesis is true. If the null hypothesis is true, I expect a value somewhere near the peak of the distribution. The null hypothesis is saying, oh, it's 0.5 right here in the center, 0.5, let's say. I should get a value here. If I'm going to reject the null hypothesis in this case, the case where the alternative is greater than 0.5, where would my value land on the spectrum where I would say the evidence is supporting this? To the right. The evidence, the data point that I get, my actual data should be somewhere on the far right if I'm going to reject equals in favor of greater than. If, on the other hand, my alternative is that it's less than 0.5, then where would my data point fall for me to reject the null hypothesis now? Somewhere on the left. And we'll have to figure out precisely where the cutoff point is. What's the exact number where I say, well, if I fall past that, I'll reject the null hypothesis, and if I don't fall past it, I won't reject the null hypothesis. We can actually our calculators can get the exact number to the 10th decimal place. Past this, reject. Not past this, don't reject. We'll see how in a few. In option number 3, where I'm going to reject the null hypothesis in favor of the alternative where it's not equal to 0.5, where would my data point have to fall for me to reject it now?
It wouldn't fall in between.
No, if it's in between, it's a likely result.
Would it be given to both sides?
Both sides. In the case of not equal to, any results on the far left or far right would lead me to conclude that the null hypothesis is most likely wrong, and therefore I'm going to reject it. So we call this a right-tailed test, a left-tailed test, and a two-tailed test for the hopefully obvious reasons. Right-tailed, left-tailed, and two-tailed.
Are you gonna tell us how to do it on the calculator?
I will. Oh my God, yes. In fact, why would we ever not want to use our calculator for this? Since the calculator can do it in seconds, when it would take us more seconds, possibly even minutes to do it. So yes, we're certainly going to want to use our calculator for this. And in fact, if you take out your calculator, even if we're not going to do this yet, just this second, but if you go to stat and then you go to tests on the right, we already saw last time that we had lots and lots of intervals. We only used the 1 proportion z interval so far. But how many intervals were there on the list? We didn't use them all. But if you go to stat and over to test and you scroll down, how many different intervals are there?
4.
I think more than 4. Is there only 4?
6.
6, I think, right? 6 intervals. So there's 6 different scenarios. We only did 1 so far. The 1 proportion z interval is the only one we did so far. But there's a total of 6, and by the end of the semester, we'll do all of them.
Okay.
Well, the whole rest of the semester is just different confidence intervals, different hypothesis tests. So the basics are the same, and then just different situations. Now, what's above the intervals? Stat test, all the way to the right. Stats, and then go right to test. So look at your calculator. What's above the intervals? All these tests, correct?
Yeah.
So let's pick one at random. Let's pick this chapter. Is there a 1 proportion z test?
Yeah.
So let's go to the 1 proportion z test. And even though we're not going to do it yet because we don't have all the information, look at the bottom of that. When it comes to less than, greater than, or not equal to, you all see the 3 options there, correct?
Yeah.
So for every problem that you're given, you have to figure out what your alternative is from the information provided. Notice that they're all not the equal sign because the equal sign always goes to the null. And depending on the specific problem, you'll depend on which of those three that you're going to pick. What other information is required there for that one proportion Z test?
B0.
The confidence.
We need P. No, there's not a confidence interval. This is a test. Nothing to do with it. Two completely different things. We need P. That's going to be the null hypothesis assumed value. In this contrived example, it's 0.5, but in every other example, it'll be something different. But we have to know what the null hypothesis is claiming the true value is. What else do we need? N. What do we think N is? Well, we take a sample. That's where our data comes from. So we need N. We need the sample size. And then what's the last thing we need? X, the number of successes, which is again something that comes from the sample. So P, that's a null hypothesis. Less than, greater than, or not equal to, that's the alternative hypothesis. N and X, that comes from the sample. Once we have all of that, you plug it all in, and out pops our answer. Now we have to understand how to interpret the answer. The calculator is not going to say reject or don't reject. We have to take our numbers that we get at the end of the problem and determine whether we reject or we don't reject, and I will explain how. But are there any questions so far? Yes?
Would we have to use all like the less than, greater than?
No, there's three different examples.
Yeah.
Every problem is different.
Okay, it just depends on the problem.
It depends on the problem. If I say, you know, I'm going to Subway a lot, and they claim that their sandwiches are a foot long. And I went there 10 times. And every single time, my sandwich, I had a ruler with me. I carry it with me wherever I go. Every single time, I measured my sandwich. And I'm sorry, but it was not 12 inches. In that case, this is not a proportion. This is a mean one, but conceptually, in that case, would my alternative be no, I'm sorry, it's greater than, less than, or straight up not equal to 12? In that case, it's less than. If it's greater than 12, I'm happy. I don't care. Right? The more the merrier. Right? So I have to realize that in that example, I'm testing to see whether or not it's really less than 12. They didn't tell me the problem is going to be that. I have to understand what they're asking and figure that out. Yes?
Would it also be the not 12?
Well, but it depends on, it's not that it can't be this. It's what are you testing for? You're not testing to see if it's less than or greater than. You don't care if it's greater than. You're happy if it's greater than. Your test is to say, is Subway lying to me right now? And it's really less than 12. Because if they're lying and it's really greater than 12, you wouldn't care, right? You're not going to care if it's greater than 12. In fact, you would even say that they're lying. You would just say, well, they meant 12 or more. But if it's less than, now they're lying to the consumers. Now we can get the Better Business Bureau involved. We can do false advertising. We can sue them for everything they're worth. And they will join Jared where he's at right now. So the point is that you have to figure out from the question whether it's less than, greater than, or not equal to. Yes?
Could somebody also just interpret it as it's not equal to 12?
Sure, but their results might not be the same as yours.
So how do you differentiate?
You have to just, I mean, listen, you're a statistician. You can do the statistics whatever way you want, but then you have to interpret the data at the end. Someone will look at your data and say, you're a bad statistician if you're doing not equal to here, but mathematically you can. I can even do this. I can do greater than. It's just the results are not going to tell me anything interesting.
So in the sandwich example, how would you use non-equal to? Like how would...
Well, again, let's do some examples. You'll see it in action. You'll see it in action. Okay, so the question is, how do we interpret our results? So to do that, I'm going to pick an example from the book. And we're going to look at the results from that example. And then I will explain to you how to interpret your results. So let's do the following example. And we'll do it on the calculator, because why do it by hand if we don't have to? Okay, so this is an example. It says, can we feel the future? Precognition is the conscious awareness of a future events that could not otherwise be anticipated through basic reasoning. Does anyone here believe on a personal level that there are people out there with the ability to see future events in some way, shape, or form. Okay, I personally don't, because there's no evidence for it. So it's supernatural, and therefore, listen, I believe in things that I believe in God, and I'm never gonna be able to prove that. It's a belief. I personally don't believe in this. If someone comes tomorrow and shows me proof that it's true, I'll be like, okay, I was wrong. It's not like it's a, core belief of my entire identity. Yes.
But yeah, people do how do you predict the weather?
No, the way we predict the weather, no. Predicting the weather is very simple. What the meteorologists do is they look at the weather that day, and they say, okay, it's this temperature, it's this humidity, it's this cloud coverage, the winter doing this, the winter doing that, whatever the case may be. And then they look through hundreds of years of data at every day in history that they have, at least, where the weather conditions were about the same. And they see that out of all those days where the weather conditions were like this, it rained 70% of the time. Therefore, there's a 70% chance that it will rain tomorrow. Well, that's why they're not always right. Okay, but that's how they do it. They don't, they use empirical data. They use past information to predict. Okay, but we're talking about someone saying in 18 seconds, a 7-foot tall Amazon woman is going to walk in that door. And then she does. Okay, you'd be like, okay, how did he know that? Okay, and either I planned it with her in advance, which is what would happen. If that actually happened, that's what I would believe, that it was just planned in advance, or I somehow saw the future. Anyways, we're going far afield. The fact of the matter is, okay, so the researchers reported that in 5,400 trials, stop, what do I have? My sample size, 5,400 trials. Participants selected some, I didn't finish reading the first paragraph, it's about this long, and it's about being able to predict something. So participants selected the target 2,790 times. So what is that? That's the number of success, not the success rates. What did I say, 2,790 times. So that's how many of the 5,400 were successes. Okay. Now, we want to see whether or not there was any result here that is, and apparently the case may be like there were 2 cards and they picked one of the 2 cards. So 50-50 chance of picking the right one. Now, purely by guessing, even if there was no such thing as a supernatural this or that, could people guess the right one by accident?
Yeah.
Sure. So if there's no such thing as precognition, what percentage of the people would guess right? What do you think it would be? It would be 50%. Half would guess right, half would guess wrong, right? Pure guessing, 1 of 2 chances, right? So in this case, without them telling me, my null hypothesis is that the true percentage of correct guesses is 50%. It's a 50-50 chance. Why wouldn't it be that? Yes.
So if they were like, they have to pick between 3 cards, or not hypothesis would be 0.33.
It would be 1/3. In this case, undergraduates, volunteers at Cornell University were tested to see if an unconscious need to avoid negative experience could stimulate precognition. Participants were shown a picture and its mirror image side by side on the computer screen and were asked to indicate which image they liked better. So a picture and its mirror image. And it said, which one do they like better? If the participant indicated a preference for the target to be, the computer flashed a positive picture 3 times on the screen. A positive picture is one that has been previously identified as evoking positive emotions, like a cat dying or something like that. Okay? If the participant, I had to, okay. If the participant indicated a preference for the non-targets, the computer subliminally flashed a highly arousing negative picture, one evoking negative emotions. The researcher was interested in whether over the course of the experiment, Precognition will be strengthened by an unconscious desire to avoid the negative emotions evoked by the negative pictures. In other words, I'm getting really negative when I'm doing this. So hopefully subconsciously, I'm able to pick the right one. That's what we're testing. So if there's absolutely no way of determining which is the right one or the wrong one, I would expect to be right 50% of the time. If, on the other hand, people have the ability to have this future knowledge subconsciously, what would the proportion be?
Not 50?
Huh?
Not 50?
Well, more than 50%. It should be, the whole point is it higher? So this would be a right-tailed greater than 50% experiment. Right? If people can really do this, they should pick the right one more often than not, right?
Yeah.
Now, again, they didn't tell you that in the problem. You have to realize that that's the point of the experiment. With this information, we can now go to our calculator. And our calculator will give us some results. So let's go ahead and do that, huh?
For P, we put 0.5.
Say again?
For P, we put 0.5.
P will be 0.5. This is the one proportion z-test. P is 0.5.
Is this number 6 on the calculator?
I already passed it, I'm not sure. But it is the one that's labeled one proportion z-test. And it's the greater than one.
Is that the one eating for P, or is it the one? Eating it.
One that looks like this.
You said Z-test?
The one proportion z-test. The one proportion z-test. Calculate. Although drawing it is also informative. So you should do both one after the other just to see it. But let's do calculate first. What are my results?
Z
No, not z hat, z.
equals 2.34.
2.449.
P equals 0.007
What?
and P hat is 0.516 bar.
We have to get P 007.
They gave me that in my calculator. You don't have P? P is the most important one there. Out of these three numbers,
We
P,
didn't have the other two, correct? The
what do you have there?
0.9928.
0.9928.
That's P though.
There's no 0.9928.
Well, yeah.
What the hell? You did a less than, it's a greater than.
I thought you didn't appear.
I don't know what that means. I pointed to it. It's the openings on the left side.
Yeah, but I said eating or do away from the P.
I didn't know what you meant.
Yeah.
I didn't know what you meant.
Well, like when you see the alligator.
So now I wrote these numbers down. Also go back to the same test, just even though I don't normally do this because I don't have to, go ahead and hit the draw button instead.
The draw button?
Yeah, instead of calculate, hit draw and see what it shows. When you hit draw, what do you see?
Invalid.
What kind of curve? I'll see yours in a second. What kind of curve?
Bell curve.
Bell curve.
So you 0.5.
And which part of the bell curve is shaded?
Right.
The far right. Okay. Now yours doesn't work.
Interesting.
Does this not work? I have no idea. Worst case, let's cut that one off. I turned that off. Yours. Kids these days. There you go. Okay, so yes. Huh? You had less than 50 grade.
How does it look like that? Why does it less?
Because it's greater than this number.
Oh, it's here. Oh.
Okay, so let's go through these numbers. Guys, let's go through these numbers. First, this one, p hat. That's the easiest one. 0.516 bar. What is p hat referring to? The reason why I asked this one is because it's not new. We've done this 100 times. What is it? It's a sample proportion. You can actually do that by hand. It's just x over n. That's just the actual proportion of the true guesses in the sample. 50% is what we were thinking it might be. You got 51.6%. Is that in the vicinity of 50%?
Yes.
Yes, right? So if I got something like that, I might say, well, it's a sample. It's pretty close. I mean, I can't imagine it's going to be exactly 50%. Even if I flip the fair coin 100 times, it's not going to be exactly 50-50. It'll be in the vicinity. So p hat would seem to indicate that the null hypothesis is correct. It's around 50%. However, p hat is not the picture. We don't care about p hat. Because the bigger the sample size, the more accurate our results are going to be. So this might be, even this might be too far from 0.5 when the sample size is this big. So it's not p hat that you want to look at. It's p that you want to look at.
Question, is that every time? It's always gonna be P not P not? Or
Yeah,
does it
yeah,
change?
every time. This is what's called the p-value. Every experiment has the p-value. This is the one and only numerical result that you need to come to a conclusion about the test. You can do it from Z, and I'll show you how, but you cannot do it from p hat unless you do like more math. We want to use the calculator. We want to do as little as possible. The p-value summarizes everything. Yes.
Going back to p hat, so you said 0.51 is pretty close to 0.5, right?
Yeah.
So what's the threshold for that is?
I'm going to show you.
Oh,
I'm going to show you. You can't do it by eye. P hat looks close, but looks can be deceiving when the sample size is so big, because the bigger the sample size, the more accurate we expect the results to be. So with a sample size that big, we might be too far from 0.5. And the fact, as we're going to show, we are too far from 0.5. And it's the p-value that tells me that. Here's what the p-value means. Essentially, if the null hypothesis were really true, this is how likely you are of getting the result that you got. What percent is this? 0.7%. If the null hypothesis were really true, we have a less than 1% chance of getting the result that you got. Now, if you did something and something that has less than a 1% chance of occurring actually occurred, would you be surprised?
Yes.
Would you be surprised to the point where you might say, I don't think my underlying assumptions might be incorrect here. This is the whole idea of a p-value. If the likelihood of getting the result that you actually got from the experiments is small, under the assumption the null hypothesis is true, we might want to reject the null hypothesis. How small is small? How small is small enough that we say if our p-value is less than this number, we reject the null hypothesis? If the problem does not tell you, take 5%. Just like for confidence intervals, what was our default confidence? If they didn't tell us, 95% confidence interval from here to here. Now it's the outside part. Our default is 5%. whether it's one-sided or two-sided, but our default is 5%. If our p-value is less than 5%, and of course, if the problem says use a different number, use the number that they give you. But if our p-value is small, we reject the null hypothesis in favor of the alternative. In this case, the data suggests that the true value of p is somewhere greater than 0.5. Do I know where? No. I might assume it's around here, but I don't know where. Question?
Yeah, so the reason it's 0.5 is because it would be an outlier or something like it.
No, don't think about outliers here. So the null hypothesis? The null hypothesis is 0.5 because if nobody had the ability to predict the future, it should be 50-50.
Based off the confidence. You know, I said it's 95.
Oh, no, 5% is default, nothing to do with this problem. Default, 5%. Nothing to do with anything in this problem specifically. Okay?
I understand that. I'm saying based off the like you're talking about the 95% confidence that we use to tell whether a data set in the last chapter is
Yeah.
the data set. Now we're basing it off the outer 5%.
In a sense, yeah, in a sense. Basically, we're saying the result that you got has less than a 5% chance of occurring, and yet you got it. I'm going to question my null hypothesis. I think maybe there's something that's not quite right there. Small p-values make us reject the null hypothesis. Yes,
So Professor, every time that the p-value is less than 5%, we reject it completely.
unless the problem specifically gives you a different level of significance. And by the way, that's a term for it. The level of significance of the test, it's a significance test, a test of significance, it's the title of the chapter. The level of significance of the test is a percentage. And it's the number that we're going to compare the p-value to. If it's a 5% level of significance, any p-value less than 5%, reject the null hypothesis. If it's a 1% level of significance, will we reject the null hypothesis here? Yes, because it's still smaller than 1%. If it's a 0.5% level of significance, will we reject it?
No.
No, because it's not less than 0.5%. So rejecting or not rejecting depends on the level of significance. Yes,
Will they give us that?
they will give it to you, and if they don't, it's 5%.
They don't.
If they don't say anywhere in the problem what it is, it's 5%. Okay?
You said it's called level of significance.
The level of significance, and you'll usually see the symbol alpha. Alpha is the level of significance. Notice that nowhere in the calculator does it ask for the level of significance. The calculator will not tell you to reject or not reject. The calculator will give you the p-value. You look at your level of significance for the test and then decide based upon your p-value whether or not you're going to reject the null hypothesis. Yes.
5% or 0.5%?
5%, 0.05. 5%. Unless it tells you otherwise. Now, I want to be a little more precise about what I said about the p-value being the probability of getting the result that you got. Because in reality, when you have infinitely many results, the probability of any specific result is 0. So what we really mean by the probability of getting the result that you got, we really mean the probability of being in this region, past your data point. So we're not only looking at the result that you got, we're also considering anything past it. And saying, if I add up all of those probabilities, not just what you got, but anything past it as well, and it's still less than 5%, we're going to reject the null hypothesis. So the p-value, this thing here, the p-value, is the probability of getting anything past the result that you got. Now, what is the result that you got? That's your p-value. 0.516 is your sample proportion that you got. But in terms of a z-score, 2.44. Your value, or 2.545. Your value that you got is 2.45. Now let's think about it. How many standard deviations away from the center is 2.45? By its very definition,
2.5.
about 2.5 deviations out. what percentage of data is passed 2.5 deviations out? Well, let's remind ourselves, it's actually less than that. Let's remind ourselves from like what, chapter 3. If you go 2 deviations in either direction from the center, if you go 2 sigma to the right and 2 sigma to the left, what percent falls in here? 95, no, 2 sigma in other directions is 95%, correct?
Yeah.
Which means how much is here past this point right there? That's 2.5%. If I go all the way out past 2, but rather to 2.45, then it's going to be something less than 2.5%, correct?
Yeah.
Certainly less than 5%.
Yeah.
In fact, what percent is it? 0.715%. This is the probability of getting past what you got. So for Z, it's a little harder to interpret it. So I always recommend focusing on the p-value. It's the one and only one number that you need to come to any conclusions about the test. If it's less than 5%, reject the null hypothesis in favor of the alternative. If it's not, we don't. Don't accept anything. We either reject or do not reject the null hypothesis. Questions on that? Yeah.
So P is the answer to the question we're trying to solve in the book.
P is the ultimate answer. Well, the ultimate answer is reject or not reject. That's the ultimate answer. That comes directly from the p-value. So in our case, we reject the null hypothesis in favor of the alternative. The data does seem to suggest that people do have this ability to form supernatural, whatever the question was. Okay, the data supports that. If you really don't believe in that crap, then you might say, I'm going to do a new study of 100,000 people and get a really large sample size and really, really narrow in on the value, and we'll see what happens there. And then hopefully, as a good statistician, you would say, well, even in that case, the data said it does. I mean, if that's the outcome, maybe I was wrong. Those are magic words, by the way. You don't hear that often. If you're ever on the internet, there are some words you'll never hear. And those are, you're right, or my bad, or I learned something today. You'll just never hear that. So as a statistician and someone hopefully with intellectual integrity, you will acknowledge if and when you were ever wrong. I'm still waiting for the first time for me, but I promise that when it happens, I will acknowledge it. Question, yes.
So the question will ask us not what the P is? Or
The question will say, do you reject or not reject? Or what do you conclude? Right, that's what the question is going to be. What do you conclude? Right, all I had was 4 things. Oh, no, I had less than 4 things. I had the words, the scenario, what was going on. I had my X and I had my N. That's all I had. I had to figure out what the null hypothesis was, what the alternative was, then go to my calculator, have it compute the p-value, and then interpret the p-value. Okay, so that's why this is a little more challenging than confidence intervals, because there's a little more that you got to do on your own. Let's do another example. Does the order in which wine is presented make a difference? In one Canadian study, subjects were asked to taste 2 wine samples in sequence and then indicate which they liked better. Unbeknownst to the people in the survey, both wines were exactly the same. Yes? I haven't finished the question yet, but thanks for interrupting. Go ahead. Well, yeah, I mean, if they're exactly the same, and therefore people have no preference for picking one over the other because they're the same, then we would expect half the people pick the first and half the people pick the second. So this is again a scenario where H naught, the null hypothesis, is equal, where P is equal to 0.5. The parameter of interest is the proportion of subjects in the population of all adult wine drinkers who would select the wine presented first. The authors of the study want to know if order makes a difference. So what's the alternative?
P is greater than 0.5.
Would it be
Not equal to in this case. They didn't say anything about more people liking the first or more people liking the second. They just said, is there a difference? So in this case, if the null hypothesis is wrong, that means that P is anything not 0.5. It could be greater, it could be less than. Information is not provided. Yes,
Could you say the question one more time?
I will read it again word for word. Does the order in which wine is presented make a difference? In one Canadian study, subjects were asked to taste 2 wine samples in sequence and then indicate which was preferred. Both samples given to a subject with the same wine, although the subjects were expecting to taste 2 different samples of a particular variety. The parameter of interest is the proportion P of subjects in the population of all adult wine drinkers who would select the wine presented first. The null hypothesis is that order makes no difference, and thus that half the time the wine presented first will be selected. That is, P is equal to 0.5. The authors of the study wanted to know if order makes a difference, but did not specify whether first or second wine would be preferred. So what is the alternative? If it's not 0.5, it's not equal to. They didn't say we think it's more or we think it's less. They said not equal to. Now, I am not a wine drinker per se. I am not a sommelier. How do you pronounce that word? Sommelier, right? I went to wine country with a friend some months back. Wine sucks. I can't drink that crap, but still, I hate it.
Yes.
I hate it. The only thing I drank was like dessert wine that has like no alcohol in it, you know. Anyways, but apparently these wine sommeliers are just crazy. These the best in the world. Like they can give them a wine and they'll tell you what wine, what year, what harvests. Apparently it's a real thing.
They don't drink it, they just taste it.
They taste it, and then these are the ones who work, they get hired for restaurants, and they match your meal with the right wine for your meal to enhance they get paid a crap ton, but, huh? What? Well, if the people who eat at that restaurant don't like it, they're not gonna come back. It'll be,
Like they tried, like, they ate the food with like a bunch of different wines and they're like, I think this one,
I see.
You're not actually thinking too deep into it.
I understand. I'll bring it up at the next convention. We'll find out what the answer is. Okay, so I don't have an answer for you. I don't know. I'm not a wine drinker myself. All right, so anyways, in this experiment, it goes on to the next chapter, next section. We have let's see how many it is. We have, oh, that's the wrong one. I did question 17.3. So did they do 7? Here we go, 17.3. So there were 32 subjects in the study. N equals 32. There were 32 subjects in the study. And a total of 22 of them thought that the first wine was better. X equals 22, because remember what we're looking for is the proportion of who liked the first wine. So 22 of the 32 said, I like the first wine. So now that we have all the information we need, let's go to our one proportion Z test, put in our data. What is our p-value? 0.0339 approximately. As a result, what do we conclude? At the 5% level of significance, we reject the null hypothesis. And apparently, it's not 50%. The data supports the fact that it's not 50-50. We don't conclude that more people like the first, even though the data certainly seems to support that, because we didn't test that. We didn't test if it was greater than. We tested if it was not equal to. And the result of our experiment for it not equal to is that you're right. The data seems to support that it's not equal to. What if instead I said, no, that wasn't the goal at all. I was really curious whether more people like the first one. How would that change the experiment? Only one change. What would the one change be if I really came along and said, I think more people like the first one? Then that would change the alternative from a not equal to a greater than.
And then, so wouldn't the data support that?
Well, let's take a look. We got to go back and redo on our calculator. We got to make one change. What's the one change we got to make? Greater than. Everything else is the same, so I'm just going to write the p-value here. What's the p-value? 0.0169. That's even smaller, which makes a lot of sense because our data was definitely skewed in that direction. Right, 22 over 32. What was our p-hat for 22 over 32? It's still there now. What was our p-hat? 0.6875, right? 69% of the people seem to like the first one more. So our data is certainly more in that direction, right?
Yeah.
So I would reject the null hypothesis and be a lot more confident in my selection in this case than I was in this case, because the p-value is even lower, right? The lower the p-value, the less chance of getting that result if the null hypothesis were true. So the smaller the p-value, the more inclined I would be to say, sorry, I'm not jiving with the null hypothesis here. So both the two-sided case and the one-sided case both gave me a conclusion of rejection. This one with a little more certainty. Okay. What do you notice about these p-values, by the way? Kind of hard to see because I'm rounding a little bit, but take a look at those p-values. Tell me if you see any connection between them. It's more than that. I don't mean where they're different. I mean, look at the actual numbers. Yes, this is exactly half of that. Exactly half of it. Exactly half of it. I mean, we're rounding here. So if you went out 10 decimals in your calculator, you'd see it's exactly half to 10 decimal places. But the p-value for a one-sided experiment is always half the p-value for the two-sided. And the reason is this. For a one-sided case, I'm looking for being past my data point. My z-value here was 2.12. So for a two-sided, for a one-sided case, I want to see if I pass 2.12, right? If it's two-sided, I want to see if I'm past 2.12 on this side, or equally past negative 2.12 on that side, because either way, I'm past my data point. And by symmetry, the total of these two areas is precisely twice the total of 1. So the p-value for a two-sided experiment will always be, for these types of tests, twice that of a one-sided. In fact, in this course, I don't think until maybe the end, when we get to the chi-square test, that might be the one time this is not true. But until then, all the things, all the intervals, all the tests that we're going to do, not intervals, but the tests, there's 6 of them. 1 proportion z in a test, 2 proportion z test, the t test, the z test, the 2, they're all going to have the case. The p-value for a two-sided experiment is twice the p-value for one-sided. Question so far? Okay, so what I want to do now is do something which is in the book, could be asked on it in tests, but isn't completely necessary because once you have your p-value, you're done. And that is, how does your calculator get the p-value? How do we do this by hand? We're going to do one with the calculator and do one by hand, compare the results, be confident we know what we're doing and that we got it correct, and then never do it by hand again. Yes?
Is it just x divided by n
Is what x divided by n?
to get the p-value?
No, that's p hat. P hat is a sample proportion. The p-value is the probability of getting what I got or something past it. 2 completely different things. Let's recall how many p's we have at this point. We have p. What does p stand for? The population proportion. That's a true value. My null hypothesis is making claims about the true value. I believe the true value is this. No, it's this. But the null hypothesis is always making claims about the true value. We have p hats. What is p hats? The sample proportion. That's what I got from my sample. We have the p-value. That's the thing that we just saw. The calculator just calls it p, but recognize that it's not the same p as that p. It's the p-value. We have p-twiddle. We saw this last section, which was a modification of p-hat for small sample sizes. And we have one more, p0. Oh, and we have p star. All right, we have p star. What's p0? So one thing I haven't mentioned yet, but you've seen it all today. Because your calculator, you used your calculator at all, the greater than, the less than, or equal, not equal to, what was next to it? P0. P0 is your claimed belief about what P is equal to. I believe the true value is this. Does that make this a true value? No, it's just my claim. So P0 is your claimed belief about what P is. Yes,
Is it supposed to be P star or Z star?
both. We had Z star, we had P star. We had both of them last time. So we have 6 different P's. And you're in luck in some sense, because I don't think there's any other ones this semester. So we're not going to keep adding to the list. I believe these 6 are all of them. Yeah, they're all contextually different. You got to know what they are. When I say it, hopefully it's clear. Hopefully you remember it on a test or a situation. But those are the 6. So let's do an example where we do it on the calculator, and then we do it by hand. We see that we get the same results. We go home and decide to live lives of religious fulfillment. So let's do a question. And we'll do it both ways. Okay. Are boys more likely? Are they more lucky? Are they what's? I just read the question. Are boys more likely? Let me just go further. Huh? Okay. We hear that newborn babies are more likely to be boys than girls, presumably to compensate for higher mortality among boys in early life. Is this true? Jesus. A random sample collected in 2005 found 13,173 boys. What did I get? What is that? X? 13,173 boys among 25,468 firstborn children. What do I have? 25,468 firstborn. So we only care about firstborn in this experiment, right? So we have to understand the context. This is not just are boys more likely in general, but specifically for firstborn children. So based upon the question, what's my null hypothesis and what's my alternative?
P is greater.
Wait. What's my null hypothesis first? P equals 0.5. If it's not true that boys are more likely, the status quo, the common sense proportion will be 50-50, right?
Is the null hypothesis always 50?
The equals not always 50-50. Every example that we've done has been 0.5, but I'm not promising you won't see one that's different. And the alternative is that P is greater than 0.5. Are boys more likely? Is it more likely for boys to be born than girls for firstborn children? So let's see what the data seems to suggest, both by hand. 13,173 25,468. This is a greater than calculate. So what is my p-value?
1.8.
What is my p-value?
You're what?
What is my p-value? Because no one said has said it correctly yet.
180.99.
No one, 0.99.
1.88 times -8 to the power of -8.
Closer. Look at your calculator. It says, it should say, if you did it correctly, 1.8853522327 E -8.
Point,
Wait, what does E -8 tell you to do?
like.
Move the decimal 8 spots to the left. So the p-value here is 0.000000 through seven zeros, followed by approximately a 2.
That's what it means.
E -8 times 10 to the -8 power. That means you move the decimal place 10 spaces to the 8 spaces to the left. So that means to the 1 and then 7 more. So you should have 7 zeros. That means if the null hypothesis were true, if P is really 0.5, this is a chance of getting the result that I got. If something this unlikely actually occurred, would I accept this? Would I think this is correct? No. So I will certainly reject the null hypothesis in this situation. And it seems that yes, amongst newborn children, from the sample at least, boys are certainly more likely to be born than girls. Yes.
Wait, that means it is true or it's not?
I reject the null hypothesis.
So it's not.
P-value is small, reject.
More boys aren't born.
Huh?
So there isn't more boys.
So the alternative is that boys are more likely. I will reject this in favor of this. My conclusion is boys are more likely. I will conclude P is greater than 0.5. There's more than 50% chance. When the null is low, when the p-value is low, the null must try to rhyme a little bit. When the p-value is low, the null must go. When the p-value is low, the null must go. When the p-value is high, let the null fly. So when the p-value is low, the null must go. When the p-value is high, let the null fly. Let's all have some pie. I don't know what you want to say, but the point is, in this case, we reject the null hypothesis. Now, Z, according to the calculator, yeah? Z, according to the calculator, is what? 5.5 or so, 5.50, which, as you can tell, means we're 5.5 deviations to the right. That's really way out there. Again, a very unlikely result, reinforcing the fact that we're going to reject the null hypothesis. The question is, can I get these results by hand? And the answer is yes, in a very simple way. We have a formula for Z, which I'm not going to derive, I'm just going to give it to you. This is the formula that your calculator uses. It's P hat minus P0 divided by the square root of P hat 1 minus P hat over N. You might recognize that square root of P hat 1 minus P hat over N because the same thing appears where? In last chapter for confidence intervals. And that's not a surprise. We're basically calculating the Z-score, where we're taking our data point, subtracting the mean, and dividing by the standard deviation. That's essentially what we're doing here. We're creating a Z-score. So let's just do it here quickly. P hat is, how do I calculate P hat? It did say it, but if I'm doing it without my calculator now, I want to do it by hand. Right? X divided by N. So what do we get for our P hat? 0.51723737174. Any further calculations on my calculator? I want to use all these decimals for maximum accuracy. I don't want to type in 8 decimals every time. All I need to do is move my cursor up and hit enter on that number, and it will just recall it. So I'm going to do that number minus 0.5, enter. That number now that I have, that's my numerator. Divide by the square root of that number times parentheses 1 minus that number over n, which is 25,468. Enter.
Is there a time like we won't be able to use calculator and we'll have to?
Well, if you're ever stranded on a desert island, you might not have a calculator handy. What will you do then?
Well, I'm not gonna be doing all this. So they have-
I mean, who knows? They did it on Lost.
Oh, they did.
Well, they could have. You never know. You didn't watch the TV show. How do you know? Well, there were times that they were fiddling with numbers.
Yeah, but not like that.
Maybe they were. It wasn't on TV because everyone would be bored by it. Okay, they had to pick and choose what to show. Okay. Anyways, sorry. This is a sore point.
Do you like Lost?
Do I like Lost? Do I like? Yeah, I a little bit. Yeah. So, what do we get? What did my calculator give me?
5.5.
5.50.
Nice, guys.
Okay. Hey, we're 1 for 10 now. Good. So it gives us the same z-score. Why do it by hand? The calculator gives it to us. How do I get the p-value once I have 5.50?
Oh, wait.
How do I get the p-value now? How do I get the p-value? Don't multiply by anything.
Use the calculator.
Well, not the well, I'm going to use it to do my calculations, but I'm saying without just putting things in and having it do it for me. What math should I do on my calculator? So let's remember what a p-value is. If you look at your distribution, it's the probability of being past your z-score, of being past your test statistic, what you actually got. It's one-sided, so I only care about being past 5.50 on the right. So where on my calculator should I go? I guess at the end of the day, we will use your calculator. Where on my calculator do I go to calculate the likelihood of being past 5.50? Of what? Where do my calculator do I go? Huh?
95%.
Ah. Ah. Which one?
CDF.
Which one?
CDF.
Which one? Normal CDF.
You'd only be using one CDF.
Well, I still want to know which one. What's my lower?
5.5.
5.5. What's my upper?
You know, the,
9.01. What do I get?
0.00002.
Well, at least you're getting this part. I'm happy.
what other CDFs are there?
Binomial CDF, Poisson CDF. There's lots of CDFs. Any distribution has a CDF.
How many CDFs are you using?
Just one.
Oh.
Okay, so are there any other questions for this chapter? Because that is it. I want to go home.